Okay, thank you very much. The talk is about Langevin dynamics or stochastic quantization of Young Mills in 2D and 3D. So when we talk about Young Mills, there are two classes of questions. The first is the small scale question, which is how can we define things in continuum. The second class of questions large scale questions. Right? So I focus on the first kind of questions. So this is based on two papers with Chandra, Chevyrev, and higher. So about the large scale, we can also ask, for example, error log, confinement, mass gap, and so on. We can also use stochastic dynamic or stochastic quantization to answer some of these questions. In fact, we also have a few papers about this, but in this talk, we don't have much time to discuss that. Okay, so before Young Mills, it will be helpful to revisit Brownian motion. So this is an n-dimensional Brownian motion. It has symmetry, which is a rotation invariance. Okay, so in other words, I have a rotation group acting on Rn, and the orbits are the spheres. And the rotation invariance means the following: if I start the Brownian motion from this point, right, and project Brownian motion to the space of orbits, then I get a process on the space of spheres. If I start another Brownian motion in the same orbit, and again project the space of spheres, then that has the same law as the first one. Okay, so the Brownian motions induce the same stochastic process on the space orbits. Okay, this is because of the rotation invariance. And there is an invariant observable here, which is a norm of X. So every space, every point in this space has a notion of distance from origin. And this is invariant observable in the sense that it takes constant value on each orbit. Okay, so the Young Mills process or stochastic quantization Young Mills is an infinite dimensional nonlinear generalization of this picture. Okay, so the state space will be infinite dimensional, and there will be an infinite dimensional symmetry called gauge symmetry. So these are the orbits of this group action. And we're also going to have an observable, which is called a Wilson loop. I'll define that later. The Wilson loop also takes constant value on each orbit. The stochastic process is given by nonlinear stochastic PDE. Okay, so this SPDE arises from the so-called stochastic quantization procedure originally proposed by President Wu. That's a gradient flow of the Young Mills functional. I'll also define this later, perturbed by a space-time Y noise. And in the end, I'm going to show that I can project this solution to the SPDE in a gauge equivariant way to the space of orbit. That's like the Brownian motion. Okay, so before Young Mills, I'll just give some examples of stochastic quantization, starting from the linear case. So suppose we take a functional which is a integral or gradient u squared. Then the gradient flow perturbed by space-time Y noise look like heat flow, as the derivative of this in u is Laplace u. So we get a stochastic heat equation or sheet. And now this is a stochastic process in the dimension, right? And the state space for this process is just where we can solve the equation. So it can be, it's well known that the solution lives in this space, the Holder Bessel space, with regularity negative d minus 2 over 2. I'm not going to precisely define this space, but all we need to know for the rest of the talk is that if the spatial dimension is 1, then this solution takes value in C1/2 minus C alpha for any alpha less than 1/2. So that's the usual Holder space. If the dimension is 2, then this takes value in C0 minus. It's a space of distributions. Okay, so it's generalized functions, not continuous. And space, if the space dimension is 3, then this becomes more singular, minus 1/2 minus. Okay, so this dynamic also has an invariant measure, which is a Gaussian free field, GFF, also supported in the same space. Okay, this equation doesn't have any infinite dimensional symmetry, but it'll be useful to keep this in mind later, because eventually I'll show that the Yang-Mills dynamics is just the SHE plus something more regular than this. Okay, in some sense, the SHE, the linear equation, is a leading part of the stochastic Yang-Mills. Okay, so the next example, we're going to have an infinite dimensional symmetry. The functional now is not, so now the field is a vector field, has two components, A1, A2, and the functional is the L2 of the curl of this vector field. We write down the dynamic, the gradient of that is some linear terms like this, and C1, C2 are two independent Y noises. Okay, so now this equation or this system has a symmetry, which is the abelian gauge symmetry. If we shift this vector field by gradient of any function, then this is invariant. For example, we can check on level of action, right? So this curl of any gradient is 0. So this action doesn't see the shift. Okay, so you can also check the equation is invariant. Okay, this is an infinite dimensional symmetry because f is any function. Okay, there's a invariant observable, right? Invariant under this gauge transformation, which is I take any loop in the plane and integrate this vector field along this loop. This is invariant because the loop integral doesn't see the gradient. Okay, so so this is our SPDE, but there's a small issue with this equation, which is it's not parabolic. So parabolic PDE theory doesn't quite apply. Okay, this operator here, not Laplacian. But the idea is that we can actually add an extra drift gradient of divergence of A into this equation. This extra drift plays two roles. First of all, with this drift, the new equation is gauge equivalent with the original equation because this is a gradient of some function, right? So this is just gauge transformation. Second, we gain, so with this extra drift, the equation becomes parabolic. In fact, all these terms plus this term is a Laplacian. This is called the Turk trick, originally from Ricci flow, and then Donaldson used this trick to Yang-Mills. Okay, so the Yang-Mills equation will be a nonlinear version of this. The field A is still a vector field, but each component AI takes value in Lie algebra G. So capital G is Lie group, G is Lie algebra. The action now is L2 of a so-called curvature, which is a nonlinear generalization of curl. So it's just okay, it's a two-form. The IJ component is a curl plus a nonlinear term bracket AI AJ. The bracket is a Lie algebra bracket. So the gradient flow of this is a Laplacian. Okay, now it's not quite Laplacian, but I already added the extra drift. Okay, so it's a Laplacian. And with nonlinear terms, which look like a bracket of ADA or AA. And Ci is again independent Y noises, and each Ci also take value in G. So each Ci is a G-valued Y noise. Okay, so now the gauge symmetry says if we transform the A to this, right, then the action is invariant. In fact, this, okay, if the group G is abelian, then this is basically A plus something like gradient. So it comes back to the abelian case. The Wilson loop is defined as the following. Take any loop, right, parameterized by S. Yeah, by the way, I'll work with the, I'll work on torus, two or three dimensional torus. Okay, so this is a loop in torus. So there's something called holonomy here. So I'm going to solve this ODE along this loop. When S is equal to 0, it's identity in the Lie group. And then I solve this ODE up to s equal to 0, up to s equal to 1, and then I take the trace of that. That's called the Wilson loop of A along this this loop gamma. If the first time you see this, it's okay. If you just pretend, just ignore this h here, then the h is just a line integral of A along the gamma, right? So the Wilson loop, in some sense, a non-abelian version of loop integral, in some sense. And in fact, the difficulty to make sense of this is that is precisely how to integrate the distribution along loops. Okay, I'll discuss that later. So why do we care about this, right? So of course, there's a big problem. Construct the quantum Young Mills on R4 and prove the mass gap. Earlier progress by Balaban and so on, and many other people did it right. Formally speaking, the stochastic dynamic. Okay, so formally speaking, the Young Mills in probability should be defined by a formal measure, which looks like exponential of Young Mills action, and formally this is invariant measure for the stochastic dynamic. The hope would be if we can send t to infinity, the dynamic would construct that measure. But at this moment in our result, we only prove the local result. So our time is small, and also our space is just a torus, a bounded space, not the R4, not the entire Euclidean space. Also, our dimension is smaller than 4. Yeah, it's still interesting to construct this dynamic.
And you have a mass gap, so maybe I just.
So so this talk will only focus on continuum, the small scale question. So the mass gap is a large scale question. So this is okay. So this construction only in the torus doesn't even make sense to talk about the mass gap. In some other papers, we just work on lattice. We can show a strong coupling the dynamic also. We can also use dynamic to prove a mass gap, a strong coupling. Okay, just to recap. So we have this infinite dimensional space of fields A, quotient out the infinite dimensional gauge group. We have Wilson loops, which should take constant value on each orbit, and then dynamic given by its nonlinear SPDE. Eventually, we will project the solution to the SPDE to the space of orbits in a gauge equivalent way. Okay. So it took us like hundreds of pages to make this picture precise, rigorous. So for the rest of the talk, I'll do the following. So I'll just ask ourselves something like 5 or 6 questions, like what do we need to do to make this picture precise? Okay, and then I'll describe the rough idea how we answer each of these questions. And it turns out each of the questions we need different sets of techniques. So the first question is in 2 dimensions, what is this entire state space? Okay, so forget about the dynamic. So what is the state space? We have 2 goals. The state space should support the Young-Mills dynamic in the end. And every point in the state space, we need a notion of Wilson loop. Okay. So we know that the SHE will take a value in C0 minus. But this space is too large to define Wilson loops because distributions we cannot integrate along loop. Okay. Continuous functions we can integrate along loops, but these are too small to support the Young-Mills dynamic. On the other hand, remember the Gaussian free field or or the stochastic equation, the correlation function behave like log, right? So a log singularity, which is actually integrable along a loop. So in fact, the Gaussian free field or SHE, you can integrate along loop. You can define Wilson loop. So this indicates that something between, right? So these guys are actually there in C0 minus, right? So this indicates that should be some space between C0 and C0 minus in which we can achieve both goals. And we construct this space, it's called omega. And we show that Gaussian free field is in omega. Okay, so how to construct, this is a new resulting analysis in some sense, right? So how to construct a new space? We start with something simple, impose a norm, and complete it, right? So the simple things we start with is the guys we can integrate along line segments. In particular, continuous functions we can integrate along line segments. And then we impose two norms. Okay, I'll explain what this means. So the L is a line segment, AL is the value or the integral of A along the line segment. Suppose this line segment shrink to a point, okay? Then the AL divided by the length of L is just the value of A at that point, right? On the other hand, we expect that A is distribution. So A shouldn't have a pointwise value. This means when the length of L shrink to 0, the left-hand side should blow up. The right-hand side exactly prescribed how fast it should blow up. Okay, so here alpha is some number like 0.9. You should think of alpha minus 1 as the 0 minus there. So this is a negative power. Okay, this is what the first norm does. The second norm says, so P here is a triangle, and A partial P is the integral of A along the three edges of the triangle, along the three line segments. So this says the A along the boundary of P should be bounded by the area of P to the power alpha over 2. So this is slightly smaller than 1/2. What's the intuition behind this? Okay, so basically the integral of Gaussian free field, suppose A is a Gaussian free field, right? The integral of Gaussian free field along the boundary of triangle is something like Y noise inside the triangle. And the Y noise over domain should behave like the area of the domain to the power 1/2, slightly smaller than 1/2. Another intuition for this is eventually we want to integrate along curves, right? Now we only have integral along line segments, so we will approximate the curves by line segments, and we'll show convergence, right? So how do we approximate? Okay, so we're going to take finer and finer points on the curve. So for example, if you take more points here, right, then the difference between the coarse approximation and the fine approximation are the triangles, little triangles. So this rate of decay precisely gave us the, all these triangles eventually sum up to a geometric series. Sum up, you can take a limit. Okay, and now we complete under these norms. So why is a completion in C0 minus? Okay, why can we embed this completion into C0 minus? Well, so C0 minus is spatial distributions, right? What is distribution? Distribution means we just test against a smooth test function, right? So when you integrate against a smooth test function, essentially you're integrating over the region that supports the smooth function. And if you can integrate along line segments, then you can kind of brush out this region. And then by taking the smooth function to be suitable wavelet basis, we know the regularity. Okay, that's the rough idea. And then we build a homograph theory in this space, right? Basically for these norms, and we check that Gaussian free field and SAT satisfy the homograph criteria. Okay, so this is the construction of the state space in 2D. Yes.
You wanted the alpha to be very close to 1. So do you take alpha to be a fixed number, or you mean that there exists alpha less than 1?
Yeah, there's some range you can. Yeah. Yeah. Here I think it's between 0 or 4 and 1. Any alpha is okay.
They all give the same.
Yeah, it's slightly different. So omega should be parameterized by alpha.
Okay.
Yeah. Okay. So, and then we're going to define gauge transformations on this space, right? But I'll just briefly talk about this. So if A and G are smooth, recall that this is a gauge transformation. And we can extend this from smooth A and G to, the G, which is slightly worse than C1, and A belongs to that space omega. In other words, we can bound the omega norm of the right-hand side in terms of, these norms of AG. Also, we can prove that the quotient space is metrizable. It's completely metrizable. In other words, we can define a notion of distance between orbits. It's a kind of twisted version of Hausdorff distance. Okay, so that's the two-dimensional state space, quotient space. So what's different in 3D? In 3D, the problem is that Gaussian free field is more singular. So covariance look like 1 over the distance. That's not integrable along curves. So there's no hope, and we resort to easier question, which is, can we define regularized version of Wilson loop? So we take a in that singular space, modify that, become smooth, and then we throw that into the definition of Wilson loop. This might sound a little bit trivial because all the difficulty is about singularity of the A. It's not, because we want the Wilson loop to be gauge invariant. The usual way of regularize this, convolve with a bump function, for example, would break the gauge invariance of the Wilson loop. Right? And for example, another way to regularize A would be just run the heat flow starting from the A. Right? So the heat semigroup on A, for any positive delta, this would be smooth, but this is not gauge. So this is not a gauge invariant. The idea is actually use the deterministic Yang-Mills flow to regularize the A. Okay, so here the F delta is a semigroup for the deterministic Yang-Mills flow. And since this flow is also heat flow, it has regularization effect. So for any positive delta, F delta A is smooth. And what's nice for this flow is it preserves the gauge symmetry. So in other words, if A and A bar differ by a gauge transformation, then the Wilson loops are the same. Okay, so a similar construction also by Sky and Surov. And actually this idea kind of goes back to a paper, to some earlier papers by Langevin. But there is a PDE challenge, which is essential here. So I didn't write down the deterministic Yang-Mills flow, right? So let's try to write down the flow. So the deterministic Yang-Mills flow look like a heat equation, which give you the regularization, plus a nonlinear term like ADA. In general, we cannot solve a PDE starting from very, very singular initial condition. That's the problem. To see the problem, we can see the following. So so A0 is the initial condition, which is very singular. And if we pretend A to be just the P semigroup on A0, then the L infinity norm of this, right? So remember, A0 is not L infinity, it's worse than that. So the L infinity norm of this term should blow up when S go to 0. And actually, you can easily see that, you can kind of see that this blow up rate should be 1 over S, and that's not integrable, right? Eventually, we need to write this equation in the integral form, right? Integrate this in a Duhamel form, and if this is not integrable, then we cannot do the Picard iteration. So the idea is we actually consider a space which is slightly smaller than C minus 1/2. Okay, so I think the general philosophy in this talk is that we always design a space which is particularly tailored to the problem, and in this space we solve the problem. Okay, so now the space is this. So it's the C minus 1/2 functions such that now we impose this bound for this term. Basically says we sacrifice some spatial regularity, but we gain some time integrability. Okay, and it turns out that the Picard iteration for this SPDE will close in this space. And also it turns out that the SHE will live in that space. So this SHE is Gaussian. So we can, do some Kolmogorov type argument to prove that the SHE satisfies this bound.
You have no stochastic part here. This is just
this deterministic flow is just to regularize the connection in order to define Wilson loop in 3D. But even the deterministic PDE has this challenge, right? Okay, so eventually the stochastic Yang-Mills process will stay in this state space. So this is state space in 3D. And this is actually a nonlinear space because this condition is nonlinear. Now we are going to define gauge equivalence on this space. So we define X and X bar are equivalent if, okay, so now X and X bar are very singular, and we don't know if there is a gauge transformation sent one to another. So what do? We use the deterministic Yang-Mills flow to project them to smooth spaces, right? So now the F delta X bar are smooth. Now, if there exists a gauge transformation which sends F delta X to F delta X bar, then we go back to the singular space and say X and X bar are gauge equivalent. Okay, so that's our definition of gauge equivalence in singular setting. And the orbit space is just the S quotient of this equivalent relation. It's not quite clear that this gauge equivalence comes from a nice group action. Right? So in 2 dimension, we do have a group action on the state space, but in 3 dimension, we only have this notion of gauge equivalence. It'd be nice to improve this result. Okay, so just to compare the 2D and the 3D, in 2D, our state space is a linear, it's a Banach space. In 3D, it's actually a nonlinear metric space. And in 2D, we have a well-defined notion of group action on the state space, but in 3D, it's not quite clear if there's a group action, but we have a notion of gauge equivalence. Also, topology of this quotient space in 3D is slightly weaker than 2D. So these are the underlying space. Now we're going to run the dynamic, the stochastic dynamic. Okay, so the question: how to solve the SPDE in 2D? The SPDE look like a heat equation, nonlinear terms plus Y noise. If we forget about the brackets, then the nonlinear term basically look like a U du and like a U cube. So I just explained the idea using these 2 toy models. U is scalar. Okay, so let's look at the first U cube. Basically, this is 2 pages summary of the main ideas of SPDE. Okay, so so now 2 dimension. Okay, so we know that the linear part, right, it's called psi, has this regularity below C0. Of course, we want to, maybe formulate a Picard iteration for this equation in C0 minus, but that doesn't work because the U cube, right? So if U is an element in C0 minus, the U cube doesn't make classical sense. The idea is again to design a subspace of C0 minus in which we formulate the fixed point, the Picard iteration. Like, okay, so the subspace is the space of U, which look like psi, where psi is the solution of linear problem, plus a much better remainder, V. Okay, V is C1. We can show that the Picard iteration will close in this space. Because now if U has this decomposition, then U cube look like this, right? We still have the problem that the psi is a distribution. So psi cube, psi square still has some problem, doesn't have classical meaning. But now the problem is actually simpler because psi is Gaussian. Okay, psi solves the linear problem driven by Gaussian noise. So solution psi is also Gaussian. So now the question is how to square and how to cube a Gaussian. And this way, we can just weak renormalize them. Okay, so there's a renormalization constant C epsilon, which is essentially the variance of, okay, so this psi epsilon is a regularization of psi, right? So C epsilon is a variance of psi epsilon. And when we subtract the constant C epsilon, this will converge in probability in C0 minus. So this C epsilon is divergent, but this whole thing is convergent. Right? This is called renormalization. Now, renormalizing the Gaussian square and Gaussian cube amounts to renormalizing the equation in this way. Okay, we subtract the C epsilon, U epsilon in the equation, and then we send epsilon to 0, and we can get a limit. Okay, so so now back to the Picard iteration or fixed point. If the renormalized cube and square are of regularity C0 minus, then, well, the V is C1. The classical result in analysis says you can multiply C1 with something just slightly below C0. And the product is in C0 minus. And then the heat kernel gave us 2 more regularity. That's called Schauder theory. So if the product is C0 minus, then when we increase the regularity by 2, it's certainly C1. So we go back to this space. So we can iterate in this space and find a fixed point. Okay. Now, what about the UDU? It's more singular because of derivatives. The same ansatz doesn't work anymore. Because if V is, okay, first of all, the best hope for V is C1 because, well, the U is C0 minus, right? So the DU is below -1. Then with the Schauder theory, with increased regular by 2, it's just a C1 minus a little bit. So C1 is the best hope. But then if U decomposes into psi plus V, then this UDU, you would have a term which is the psi times the dV, and this term doesn't have classical meaning because the singularity is because of regular too low. And so this equation requires the idea of regularity structures. Okay, this is originally developed by Heyer. Heyer's idea is the following. So what is C1? Or what is CK, right? CK functions means we can locally approximate function by polynomial of degree K. And the idea of regularity structure is we should locally approximate the solution, the function, by not just polynomials, but also stochastic terms. These stochastic terms are some canonical things like a Gaussian or polynomial Gaussian. Okay. In other words, we want to generalize a Taylor expansion. Okay. So let's say if V is just C1, then as Taylor expansion like Vy is Vx times this, right? Remainder. But then we should add these terms. Okay, so what are these terms? So the P is a heat kernel, and psi is a solution to the linear problem, which is Gaussian. So basically, these guys are Gaussian, and these guys are like quadratic in Gaussian. And the regularity of them are almost 1. Okay, so the regularity of them is just slightly worse than this. And how do these terms come? So basically, it comes from here, right? So if you pretend one of the U is psi, right? So for example, if you just ignore this U and pretend this U is a psi, then this is a d psi, right? So the idea is, okay, the solution U should locally look like the d psi maybe, right? So then the heat kernel convolve the d psi is the first term. So similar, the other terms come with a similar way. Okay, so now we make this ansatz for our solution V. And we solve the equation in the space of V's, which has these local approximations. Okay, when we do that, of course, we have all the VDV and so on. So all these terms will multiply each other, and eventually we get terms like d psi times the p d psi, or something like the products of these terms. These terms also need renormalization, but we can deal with the renormalization of these terms because these are quadratic or multilinear in Gaussian. Okay. Yeah, maybe before I go on, is there any question about this? Okay, so now let's come back to Yang-Mills. It's a quadratic term and a cubic term, right? So just like in the toy models, we can solve this equation in the subspace of C0 minus of the following form. So A is the solution to the linear problem plus V, where V lives in a subspace of C1 minus, which is locally approximated by the not just the Taylor terms, but also stochastic terms. So in the end, we have something like 4 or 5 renormalizations, and turns out that all these renormalizations amount to subtracting a mass renormalization in the Yang-Mills equation. Okay, so now if you're a quantum field theory expert, you might ask, why do we have a mass renormalization? A mass renormalization would break the gauge symmetry. The reason is that we modify, okay, so we always modify the noise and renormalize and take limit, right? When we modify the noise, we basically convolve with the bound function, and this already breaks the gauge symmetry. In other words, the mass renormalization is it shows up just because the loss of gauge symmetry in the way we regularize the noise. So this is related with the next question, right? So eventually we want to show that this stochastic dynamic can project to the space of orbits in a gauge equivalent way, such that we get a Markov process on gauge orbit. So the main result we prove the following. So I didn't say this. So if we can, so suppose this is the mass renormalization, right? Suppose with this constant mass renormalization CA, we can get a limit. Then you might ask, well, you can also shift the constant C by a finite constant. That will also converge, right? So if something converges, shifted by finite, it can still converge. So which one is the right limit? We prove that there is a unique shift of that mass renormalization such that the limit is gauge equivalent. And how do we prove that? Okay, how would we prove this if this was a Brownian motion? Okay, so we started 2 Brownian motions from the same circle, and we want to prove that they project to the same process on space of circles. Well, we would pathwise rotate this Brownian motion to here. That's still Brownian motion. And since this is a Brownian this is also a Brownian motion from starting from the same point, the 2 Brownian motions should have the same law. And for Yang-Mills, we're going to do a similar thing. It turns out that we can find a gauge transformation we set by some PDE, and we apply this gauge transformation, right, pathwise to A, and we call this B. Now B satisfies the following equation, right? So the G is designed such that all the leading terms, all the deterministic terms have the same form. But the mass renormalization and the noise term are changed. Okay, first of all, the mass renormalization doesn't have is not gauge invariant, so it's natural this is changed, right? So this becomes that there's a new term here, and the noise becomes the conjugate of this noise. Well, if this is a Y noise, then formally speaking, this should have the same law, because rotation of white noise is still white noise, right? But that's not quite true because we regularize the noise by convolving the bound function. So this doesn't quite have the same law as white noise. The idea is the following. So we want to, okay, the question is what term should we subtract, or what term, how should we renormalize this term so that in the limit, this is the white noise, okay? So what we found is kind of, in some sense, the Ito-Stoyanovich correction term. When you subtract this term, this guy actually converts to the white noise in the limit. And what's surprising here is that this term we need to subtract in order to get a white noise. It has precisely the same form as this term. Remember, this term comes from here, right? So the mass normalization, when we apply the gauge transformation, we get a new term because the mass normalization is not gauge invariant. We get this. On the other hand, the white noise, this term also needs a term of same form in order to get a white noise. So in other words, if these two terms can cancel out, then we get a gauge invariant limit.
So are you saying the mass renormalization and the regularization you're using for the exceeds essentially cancel?
Yeah, exactly. The two things which violate gauge symmetries cancel each other. So in the limit,
but only in the limit, right? I mean, so
only in the limit, right? So in this sequence of approximations, we lost gauge symmetry, but we restored gauge symmetry in the limit by this argument.
So the cancellation between the two, you don't have it at any finite stage, but only in the limit it's restored, right?
Yes.
So how do I see that they cancel in the limit? I didn't quite. I mean, this looks like they cancel before the limit, but.
Yeah, I mean that's well. Actually, I think I simplified the argument too much. Yeah, so I just want to focus on the rough idea.
That's fine.
Yeah, because there's so we also need to compare this pathwise rotation of A with the other process A, which starts from here. Right? So so this is not quite that process yet. Okay, so in any case, after some calculations, we realize that this C, right, in front of this term and this C tilde in front of this term actually differ by a finite constant. In other words, if we can shift this C by that finite constant, then we're done. Okay. So this is how we restore the gauge symmetry then. So the conclusion is that there is a unique mass renormalization constant C such that the limit is gauge invariant. Okay. So I was cheating a little bit. This is not actually not a constant. It's actually some Casimir map. But when the
what does that mean?
So our noise is a Lie algebra valued noise.
Yeah.
So when we compute the covariance of them, we get an element in like a Lie algebra tensor Lie algebra, and that's the unique element in the G tensor G, which is invariant under the hadron action. So that's called Casimir operator. And when the Lie group is simple, actually that is a constant. Okay. All right. So so everything I said is 2D. Okay. In 3D, what's the issue, right? So first of all, in 2D, there are only something like 5 renormalization terms, but in 3D, there are hundreds of them.
How many?
Oh, I guess it depends on how we count, right? So many renormalization have kind of similar term if you count them together, but yeah, we didn't count. Okay, so how to deal with this situation? In fact, in the past few years, a sequence of long papers by Haier and others, they developed a systematic treatment of renormalization on the levels of algebra level or Feynman diagrams and eventually how the SPDE is renormalized. Well, for experts, the kind of algebra result is reminiscent to how Alan Kahn and Kramer built the algebra perturbative renormalization, and Feynman diagrams is in some sense you can think of that as a version of BPHZ renormalization in the context of SPDE, but of course this is there's a lot more to say in SPDE is highly non-trivial. Now this works focus on scalar valued SPDEs. In our case, our equation take a value in Lie algebra. In principle, we can also take a basis from the Lie algebra and write the equation, a huge system of scalar equations, but then we would lose a lot of intrinsic structures. So we actually extend these results to SPDEs. In the setting, SPDE is taking value in certain algebra structures, such as Lie algebra. Okay. Another difficulty in 3D is that with all the hundreds of renormalizations, in the end, we only have one term, one renormalization in the equation. That's the mass renormalization. In other words, all the hundreds of terms sum up to the same term. This is due to some discrete symmetry. For example, spatial reflection and so on. We prove some general result which says renormalization should respect to such symmetries. And another difficulty is that in this proof, there exists unique finite shift of mass renormalization such that the limit is gauge invariant. This is even harder because in this argument, we have to couple the three equations, A, G, and B, right? So because here the G, when we renormalize this term, the G depends on A, right? So so B depends on G and G depends on A. So this is a couple system equations.
Is this at all related to the deter trick?
Exactly. So the deter trick is very similar with this. Yeah. So they consider a deterministic PDE where this is not Laplacian,
right.
But then they introduce a gauge transformation which depends on the A, such that the transform equation has a Laplacian. But in our case, we want this Laplacian, both of them are Laplacian, but the idea very similar. Actually, the equation also looks similar. Yeah. Right. So when in 3 dimension, when we couple all the three equations, of course, the renormalization issue becomes even harder. But we can apply some small noise limit argument using the fact that determinist part of the Yang-Mills flow is actually gauge equilibrium. Okay, but I'll skip the details for this. So it looks like I still have maybe 5 minutes or so, right? So so maybe I can say something about the lattice since so now in this work we take a unit lattice, right? So we focus on the large scale problem, and we can also say something using the dynamic on the lattice for the Yang-Mills. So the first thing we can say is that okay, so now the lattice dynamic system of stochastic ODEs parameterized by the edges in the lattice. I'm not going to write down the equation, but we can give a new proof of the so-called Dyson-Schringer or Markinko-Mignol equations. These are equations of recursions among different Wilson loops. This derivation on the lattice for this equation was first proved by Chatterjee using Stein's method, but we give a very simple proof, a new proof, which is we just need to apply the Ito formula to Wilson loops, right? Wilson loop is just a product of the connections, and each connection satisfies the SDE. So we just apply the Ito formula to this product, to this Wilson loop, and then substitute into the Wilson loop, the SDE. And then we immediately see how the loops should deform and should glue together and so on. Yeah. So actually, yeah, very simple in case you are teaching a Ito calculus course. I want to assign some reading. This is just 10 pages paper. So
this is in a strong coupling.
This is any coupling, right? So yeah. To apply the Markov-Mignot to prove something like area law, which is done by Chatterjee, we need a strong coupling assumption. But the equation, the recursions just hold for any coupling. Okay.
You mentioned loop deform. Did you mean deformation of the loop itself or of the value of the reason?
Deformation of the loop, right? So the Markov-Mignot equation look like the Wilson loop is equal to a bunch of other loops, and those loops are, for example, deformation of this loop.
And a random walk in the loop space. With elementary.
We can think of we can think that way. Yeah. Okay. We can also use the stochastic dynamic to prove something, to prove some result about large-scale behavior and strong coupling. For example, in this paper, we show that at strong coupling, the invariant measure for dynamics is unique on the entire lattice. Okay, the uniqueness of infinite volume limit, and prove that so everything is under strong coupling regime. The dynamics also ergodic exponentially. And we also prove a version of log Sobolev inequality using Bakery-Emery condition, which says the curvature should dominate the Hessian. Oh, by the way, this is only for SO and SU. Okay. And the log Sobolev inequality implies Panguri inequality, which says the variance should be bounded by the derivative form. So now, using this kind of functional inequalities, we can prove, for example, in the large N limit, the suitably rescaled Wilson loop factorize and they actually convert to determinate limits in the large limit. And we can also prove a mass gap, which means correlation function decay exponentially again at a strong coupling. Our result improved the earlier result by Ostwalder and Seiler in the sense that our strong coupling condition is independent of N. So we can first fix the coupling to be strong and then take the large N limit. But in their paper, I think they only use the classic expansion, viewing the SON value, the field as a bounded spin essentially, and they didn't explore the curvature, the positive curvature at SON or SUN. So we get that's why we get a slightly sharper result. Okay, I'll stop here. Thank you. Questions?
In 3D, I guess the mass gap is expected also at weak coupling, right? And hope I get the predictions right.
But depending on the group, I think for
for
non-abelian compact group,
your methods in the maybe continuum give some perspective on this, or maybe Lattice.
With coupling, we don't know what to do actually. With this scalar dynamic. So that's because to prove the log Sobolev inequality, for example, basically we need to verify the Bakery-Emery condition. The condition basically says the beta, which is coupling constant, times the curvature should be larger than the Hessian of the action. So if beta is too large, in other words, the coupling is too weak, then this inequality, this Bakery-Emery condition is not true. There are some recent results by Bauer-Schmidt, for example, develop some sort of multi-scale Bakery-Emery condition. But it's not clear yet if this applies to this situation.
But your results in the continuum that you described in the beginning, they are for any coupling in any case. The existence of
Yes. Yeah.
but you're still at the short time.
Short time, yes.
What kind of obstructions do you have to going? I mean, do you have some? You must have some hope for going for longer times.
Right. So
what kind of problems are you running into?
yeah. So without the noise, that's the deterministic Young-Mills flow studied a lot by geometers, and the long time solution, at least in 2D and 3D, well known. The basic idea is to use the fact that the flow is a gradient flow. So you have a kind of natural Lyapunov function to control the flow. But with the noise, that's not true, right? Especially because we did all those kind of decompositions of the solution into, for example, linear part plus remainder. Remainder is approximated by Taylor and the stochastic terms and so on. So once we do all those decompositions, it's totally not clear how to, for example, how to use the gradient flow, or how to obtain some a priori PDE bound on the terms. But this scheme, this kind of stochastic quantization is quite successful in the case of phi 4. The results by Hoffmanova, Gubinelli, and many people. They can construct the global solution of stochastic phi 4 equation, and in this way they can construct they can give a new construction of the phi 4 theory 2 and 3 dimension.
So you're using these regularity structures. I mean,
yeah.
I guess Gubinelli has some other technique,
right? They use.
Would they also apply here, or would that be a problem?
So in 2D, I think there is an ongoing work by Sky and Young, maybe. I guess they are trying to use pair control. I guess basically it works. So
in 2D for
in 2D
for non-abelian too, or
yeah. Because in 2D we essentially only have something like 5 terms to renormalize. As I understand pair control now, they haven't got this kind of a very general treatment of renormalization. So when we have hundreds of renormalizations, I think they, unless they want to do it one by one, they don't have a general black box kind of theorem yet.
To get the dynamics on, say, R2, you take a sequence larger and larger tori somehow.
Yeah, it's usually we have to impose a weight in the norm. Yeah, so if you have some nice dissipation in the equation, then I think maybe you can, for example, in the case of phi 4, they can construct this in entire space. The reason is that the phi 4 equation has strong dissipation, like minus phi cube. This is a very nice PDE term. But here, the nonlinear term looks more like a Navier-Stokes, like a UDU. So it's yeah, even volume, it's not quite clear. I think it's a challenge.
So I mean, just missed what you have just said. So what's the reason that for phi 4 one can go to infinite time?
Phi 4 it's a nice PDE which has a nonlinearity which look like minus u cube. So once so how do you glue together local solution to get a global solution, right? Basically, we want to prove that some norm of the solution is preserved. When time is large. So this minus u cube term is such that once u gets large, this immediately impress the solution. So the solution immediately becomes under control. But here we don't have, right? For example, if the wrong sign, like plus u cube, then there's no hope. And here, the sign of the cubic term is kind of mixed between minus and plus, and also the other term UDU is a Navier-Stokes kind of term.
So So can you understand intuitively why that still enables you to get some kind of stability?
Intuitively, I would say still gradient flow. So as I said,
That would be true with the opposite side too, right? So you need to be,
Yeah.
you need to identify something that's kind of coercive for you, right?
yeah. You mean the intuition for 5/4 YAMLs?
I mean, like for 5/4, where you can see it very clearly, as you explained, but there must be such a mechanism. Hopefully, there's such a mechanism here for Yang Mills too, but it's just maybe not so obvious.
Yeah, I think. So first of all, even the Navier-Stokes term, right? So forget the cubic term in the Yang-Mills equation, just UDU. Like now Navier-Stokes with Y noise in 2 and 3 dimension. It's not clear how to construct global solution to this SPDE. So there's a recent work by Hoplanova, Zhu and Zhu. They use a convex integral, this sort of technique, get a global solution.
But these are weak. These are very weak solutions.
Very weak. Yeah. I'm not expert, so I don't know in which sense is it physical or not physical. So yeah, we did also discuss a little bit. Can we also use the convex integral to for YAMLs with noise? But the first step would be to construct some building blocks in the language of the convex integral, which is a kind of special solution to YAML's equation. But even this building block is not very clear how to construct. Building blocks for Euler or Navier-Stokes, they look very different from this type of equations.
Any call?